electric, biomagnetic, or whatever signal, they are recorded as potentials, voltages, and electric field strengths generated by different systems, maybe the nervous system, maybe from the heart muscles, or it may be the signal, maybe from the eye, right? So all these involve voltages at very low levels. So typically, the range of biosignals will be from 1 mu volt, that is microvolt, to 100 millivolt, within this range. So this low level signal will not be uh, the strength of this signal will not be sufficient for further processing or signal conditioning. Okay, so they are from high source impedances, and superimposed high level interference signals and noise may be present. So these signals need to be amplified to actually make them compatible to further processing, that is to connect these signals to devices such as any display device or recorder or AD converter, just for if you need to computerize your signal, right? So for all these, the amplitude level of these signals has to be increased. So this process is done by the amplifiers. So actually the amplifiers to measure these signals, they have to specify some specific requirements. So they have to provide amplification to the physiological signal, whatever signal is employed. They should be, the amplifier should be able to reject the superimposed noise and the interference signals, and also they should some guarantee some protection from damages through any voltage and current surges, both from for the patient and the equipment involved, whatever setup is involved in measuring the signal. So amplifier featuring all these specifications is called as biopotential amplifiers, or simply bioamplifiers. So we'll see the detail of bioamplifiers and what are the different types of bioamplifiers involved in the measuring the biomedical signals from the human body, right? So what is a bioamplifier? So as I already said, so to increase the amplitude level of the biosignals, we go in for amplification process. So with the specifications required, the amplifier which performs all these functions is referred to as bioamplifier. So the output from these amplifiers are used for further analysis. So the input to the amplifiers may be a ECG signal or EMG signal, or whatever biomedical signal that is involved in that particular equipment. Okay. So next, basic requirements of biological amplifier. So what are the features of a bioamplifier? The first thing is it should have high impedance value, right? So the physiological process to be monitored should not be influenced by any way by the amplifier. The process should not be influenced. Okay. Next, the measured signal should not be distorted. That is, no, it should not be prone to noise interference. It should provide the best possible separation of signal and interferences, and it has to offer some protection of the patient from the hazard of electrical shock. The setup should not prone the patient to any sort of electrical hazards. Then it has to be protected against damages from the equipment also, which may result from high input voltages, like say for example, uh, during the application of defibrillators or some sort of electrosurgical instrumentation like that. Okay, so every bioamplifier should consist of isolation and protection circuits to prevent both the patient from the shock and also the equipment. And the voltage gain of the amplifier should be greater than 100 decibel. The gain should always be maintained with this value. A constant gain should be maintained. Small output impedance. The amplifier should be free from drift and noise, and the CMRR should be greater than the common mode rejection ratio should be greater than 80 decibel. Okay, so so this is the basic process of the bioamplifier. So from the patient body, by the use of electrodes, the signal is picked up and it is given to the preamplifier, then a high pass filter, then the isolation amplifier, and the low pass filter. So what are the preamplifiers required and what is the purpose of using an isolation amplifier here? Everything we will see in detail in this unit. Okay. So these are the some examples of biosignals, the amplitude and the frequency ranges of the some of the biosignals. ECG, this is your EEG, ERG, EMG, and cerebral potentials recorded, and this is the action and resting potential range. So here we have the amplitude and here we have the frequency. So these are the examples of some biosignals taken from the human body. Okay, so what are the types of bioamplifiers that we use normally? A differential amplifier, this is the preamplifier might be a differential amplifier, operational amplifier, instrumentation amplifier, chopper amplifier, and isolation amplifier. So I think all these you might have already studied in LIC. So we will just have a recap of what it is. So firstly, we will see about differential amplifier. So what is a differential amplifier? What is the purpose of using a differential amplifier? And what is the output gain of the differential amplifier? We will see that now. So differential amplifier is actually, it is a device which is used to amplify the difference between the voltage is applied at its input. So the output voltage is given by V naught equals to AD into V1 minus V2. So AD is the gain of the amplifier, differential gain. If it is represented as AC, it is the common mode gain. V1 minus V2. So V1 and V2 are the input voltages. So this is a basic circuit of a differential amplifier. Actually, this is this setup. This V1, V2 to V0. This is a differential amplifier. So what will be connected to this V1 and V2? What is the input to the differential amplifier? Will be your signal from the signal generated by the electrode. It may be either, for example, we can take it as the one signal from the main electrode and the other signal from the reference electrode. So what will be the gain of this amplifier? So if you take here, V2 is applied to the inverting terminal and V1 is applied to the non-inverting terminal, and we have the load resistors here R1, R2, and the output is V0. So V0 will give you the difference of the signal, that is V1 minus V2 or V2 minus V1 depending upon the setup. So let us take this inverting terminal. So the inverting terminal, the output, sorry, yeah, inverting terminal. So the inverting terminal, the output will be V0. I think this is interchange. So V0 1, say this is the output of the inverting amplifier V0 1, which is equal to minus R2 by R1 into V1. Why we are using this negative term here? Because it is a inverting terminal. So whatever input you are giving, the input will be inverted. So minus R2 by R1 went to V1. So for if you take for non-inverting terminal, that in that case your V1 will be 0. Inverting terminal will be 0. So the when your V1 is 0, the amplifier output will be given to the non-inverting. So what will be the non-inverting voltage? So Vn equals to V2 into by voltage divider rule R2 by R1 plus R2. So this is your voltage at the non-inverting terminal. So what will be the output of the non-inverting amplifier? So this is your V2, right? V2 is the output of the non-inverting amplifier. So you take this side, it will become R1 plus R2 by R2. You take this R2 common outside, you get 1 plus R2 by R1 into Vn. So this equation 1 represents the output of the inverting amplifier. Equation 3 represents the output of the non-inverting amplifier. So we know the differential amplifier, the difference amplifier or differential amplifier will give you the difference of the signal. It will add or give you the difference of both the signals. So we can say V0 equals to V01 plus V02. That is output of the inverting amplifier plus non-inverting amplifier. So you add this to we have already known the expression for V01 and V02. So from equation 1 and 3, so you substitute here and add. So again for Vn here you replace Vn. You know the expression for Vn is V2 into R2 by R1 plus R2. So you replace it here for Vn R2 by R1 plus R2 into V2. You replace it here. So this R1 plus R2, and this here, if you take LCM, this becomes R1 plus R2 by R1. So this R1 plus R2 and this R1 plus R2 will get cancelled. So finally we have minus R2 by R1 into V1 plus R2 by R1 into V2. So you take this minus R2 by R1 common outside, you get V0 equals to minus R2 by R1 into V1 minus V2. So this minus R2 by R1 is nothing but the gain of the amplifier, and this is the difference signal V1 minus V2. So this is the output of the differential amplifier, right? So as such, the differential amplifier will give you the difference of the signal. So in biomedical applications, okay, so in biomedical applications, high gain and high impedance are attained with the differential amplifier. So usually you have to each input of the differential amplifier, you'll have a input the signal from the electrode connected. Okay, so this is the typical configuration for with the use of for measuring the biosignal with the use of this quad amplifier, differential amplifier. So if you see here, uh, the biological signal appears between the two measuring electrodes at the right arm and left arm of the patient and is fed to the inverting and non-inverting inputs to the amplifier. Actually, three electrodes will be employed. So the third one will be your what to say reference signal, that is reference potential connected to the subject or the amplifier. Okay, there will always three electrodes generally employed. So the third electrode will be the ground potential or the reference electrode. So the input to the amplifier will be consisting of 5 components. So the first one is the desired biopotential. Second one is undesired biopotential, that may also be generated. Third one is power line interference signal. So this will be of 60 hertz, and its other the interference signal of 60 hertz and its harmonics. Next, interference signals generated by the tissue electrode interface due to the interfacing. Lastly, the noise. So for all these parameters considered, the proper design of the amplifier is required. So the amplifier should provide a rejection for large portion of the signal interferences. It has to take only the desired potential. Other components the amplifier should be able to reject. So the main task of this amplifier is to reject the line frequency interference, that is either electrostatically or magnetically coupled into the subject. So the desired potential biopotential appears as a voltage between the two terminals. If you see here, the desired biopotential will be the voltage between the two input terminals. So this we called as the differential signal. So the line frequency interference signal shows only very small differences in amplitude and phase between the two measuring electrodes. So this will actually cause approximately the same potential at both the inputs, and this between the two electrodes here, it will cause the same amplitude signal, same potential at both the inputs. So it will appear between the input and the ground. So generally this signal we call it as the common mode signal, right? So the signal generated from the two electrodes is your differential signal, and other interference signal is generally referred to as the common mode signal. So the amplifier should be have the feature of strongly rejecting the common mode signal, because it is not required, it is an undesired signal, it is an interference. Okay, so here the common mode rejection ratio, that is the CMRR of an amplifier, is actually how we can say it is a ratio of the differential mode gain over the common mode gain. So the rejection of the common mode signals is actually both function of the CMRR and the source impedances. If you see here, the source impedance is Z1 and Z2. So for an ideal bioamplifier with the, if Z1 equals to Z2 and the CMRR is at infinite range, that is infinity, the output voltage is generated will be purely a biological signal, right? So the differential mode gain and the common mode gain uh, should be like it should be in the proper ratio, or we can say the common mode signal should be completely rejected. But practically it is not possible. Suppose the CMRR is having a finite value, which means the common mode signal is not completely rejected, which means it is adding some interference to the biological signal. So even in the case of ideal differential amplifier with infinite CMRR, the common mode signal will not completely disappear unless the source impedances are equal. For the CMRR to be completely rejected, so the Z1 should be equal to Z2. The related voltage drops show a difference if the source impedances are unequal. So this generates a differential signal at the amplifier input. So of course this signal will not be rejected by the differential amplifier. So the output of a real bioamplifier will always consist of desired output component that is generated due to the differential biosignal, and it will also have an undesired component due to the incomplete rejection of common mode interference signal. So this is a function of the CMRR of the amplifier. So this undesired component due to the source impedance unbalance, allowing a small proportion of the common mode signal to appear as a differential signal to the amplifier. So purely biological signal will not be generated, will not be amplified, or it is not actually possible. So we should actually maintain the source impedances to be equal. This Z1 should be equal to Z2, which is possibly we can make it to the bare minimum level. So bare minimum level is about from 5,000 to 10,000 ohms. So this actually impedances, what is the source here? The signal from the electrodes. So these impedances mainly they are caused by the electrodes. So they are not uncommon. So they should have sufficient rejection of line frequency interferences, so that the CMRR level of the amplifier should be maintained at a minimum level, that is of 100 decibel. Then only the output will be efficient. The output obtained from the differential amplifier will be mainly due to the biosignal. Okay, so to all this, your CMRR of the differential amplifier should be maintained at minimum 100 decibel, or the maximum allowable range is 120 to 140 decibel. So in order to provide the optimum signal quality and adequate voltage level for further processing, the amplifier has to provide a gain. Next, coming to gain of 100 to 50,000. So it has to maintain the best possible signal to noise ratio. The presence of high interference signals, it will deteriorate, or it will lower the quality of the physiological signal. In addition to that, it will also restrict the design of the bioamplifier. Say for example, if you take the half cell electrode half cell potential, this half cell potential will limit the gain of the amplifier. Why? Because the amplitude of the half cell potential can be of several orders of amplitude, the magnitude of this half cell potential. So this will have the tendency to limit the gain factor of the amplifier. So to prevent the amplifier from going into saturation, the components of the amplifier has to be eliminated before the required gain can be provided for the signal, whatever the signal may be. Okay, so if you see this figure, the electrodes which provide the transition between the ionic flow of currents in the biological tissue, here it is present. So they will represent a complex, the electrodes here, they will represent a complex electrochemical system. So the electrodes, they will determine a large, extent of the composition of the measured signal, right? So the preamplifier, it will play a most critical part of the amplifier itself. Why? Because it sets the stage for the quality of the biosignal. So here the preamplifier used is a differential amplifier. So the design of this amplifier is very important, because This is your first stage of the process, signal conditioning process. So here, this is the stage where the quality of the biosignal picked up is set up. Okay, so if properly designed, the preamplifier can eliminate or at least minimize the interference signals. Most of the signals interfering with the measurement of the biopotential. It will not it will not totally reject the noise. At least you can maintain the level of noise interference at a bare minimum level. So in addition to the electrode potentials and electromagnetic interferences, we have also noise generated by the amplifier itself. Okay, so the connection between the biological source, this is the source, the connection between the source and the amplifier, that connection should have a proper interfacing. It has to be taken into account while designing, because noise signals, the interferences may be generated due to this connection also. So the total resistance includes the resistance of the biological source and all the transition resistance between the signal source and the amplifier input. So they might also cause thermal voltage noise, right? So this also has to be taken care of, and proper design specifications maybe should be incorporated to avoid the interference between the source and the amplifier system. So this is what to say. These are the considerations while designing a differential amplifier to a biology to measure the biopotential. Okay, so the high signal to noise ratio, thus it will require the use of very low noise amplifiers and the limitation of the bandwidth also. So the current technology offers differential amplifiers with the noise of the voltage noise of less than 10 nanovolt per hertz signal. The current noise should be with the less of 1 picoampere per hertz signal. So both the parameters are frequency dependent. So they will decrease approximately with the square root of frequency. Okay. So the exact relationship will depend upon the technology employed in designing the amplifier input stage. Okay, so nowadays we use FET preamplifiers because they have exhibited about 5 times the voltage noise density compared to BJT amplifiers. As we already know, a differential amplifier may be designed with the help of transistors and op-amp. So here we have taken the example of the op-amp differential amplifier. We have by BJT differential amplifiers designed by transistors also. Okay, next we have the high pass and low pass filters. So these filters